So again, I knew that I'm looking at closer to 6 moles, so it makes sense it's going to take more energy to do that decomposition. Of course, that answer is D. So if I'm giving a chemical reaction, I could also tell you how much energy it takes to make 7 moles of P4 using this equation. I can do a lot of things with just this equation. So again, with these thermodynamic problems, sometimes the hardest thing is figuring out what it's asking. So let's look at this one. And you might want to read through it and then dissect what it's asking after you read through it once. So we want to calculate the work, W, pretty easy. Gained or lost by the system. So we don't know if it's being gained or lost, but we're asking for W of the system. When a gas expands from 15 liters to 40 liters against a constant external pressure of 1.5 atm. And then I give you the conversion of atm, liters atm to joules, and we want to show over. So we want to calculate our work of the system. And we know our initial volume is 15 liters. We say that our gas is expanding from 15 liters to our final volume of 40 liters. We also know that our work is equal to negative P delta V. And we're told our external pressure. That negative is important because the external pressure is, of course, the surroundings. But we want the work of the system. So that's why that negative sign is important. So what we're looking at here is we could first calculate our work. We are given our pressure. And we have our initial volume and our final volume, so we can calculate our change in volume. So our work is equal to negative 1.5 atm times our delta V. And change in volume is always, or change in anything is always final minus initial. That's what it means by change. So my final is 40 liters and my initial is 15 liters. So it's important that you understand that. Your change is always what did it end up with, what did it minus what it started with. Because if we went from 40 liters to 15 liters, we're going to have a different sign for our work. So we need to make sure we set that up correctly. So that gives us our work, bless you, is negative 37, bless you, 0.5 atm times liters. But my answers are not in atm liters. My answers are in kilojoules, so I have to do this conversion, which is pretty common that you do have to do that conversion because we typically work and heat is in kilojoules. So we can do the conversion. Negative 37.5 atm times liter. We know that 1 atm liter is equal to 101 joules, but our answers are in kilojoules. So again, 1,000 joules is equal to 1 kilojoule. But you do need to know that conversion. How many joules is equal to a kilojoule? So of course that sign is negative. So make sure you're setting up your delta V correctly. And don't forget that negative sign on P. Though you really shouldn't, because I gave you that as a given in the sheet. So okay, this one is a little bit more detailed, but not necessarily hard. We just have to go through this one in a couple of steps. So here we have a 4.98 gram sample of aniline. It doesn't really matter what aniline looks like. I wouldn't expect you to draw the Lewis structure of that because with 6 carbons, there's a lot of different ways it can be connected. But I gave you the formula, and then I also gave you the molar mass, which you could figure out with the formula, but because of time constraints, I gave you both. And it was combusted in a bomb calorimeter. So we burned it, went through combustion and bond calorimeter. And we have to know the heat capacity of the calorimeter because we need that constant, but that's given at 4.25 kilojoules per degree Celsius. If the temperature rose from 29.5 degrees Celsius to 69.8 degrees Celsius, determine our delta E per mole of aniline. So first off, we didn't burn 1 mole of aniline. We burned a lot of moles, or actually, I don't know, a lot or a little. But we didn't burn exactly 1 mole of aniline. We burned 4.98 grams sample. So when we calculate our delta E, that's going to be our delta E for 4.98 grams sample. So it's more useful to know our delta E per mole, because then we can relate that to our reaction. I don't need to write my combustion reaction to do this, but I do want you to understand that in the lab, we didn't burn exactly a mole. So at the end, once we get our delta E from the data that we're given, which is our heat capacity and our change in temperature, then we're going to need to know how many moles we actually burned so we can figure out per mole. But we don't need that 4.98 right now. So I talked about this a little bit in class, and I want to reiterate it. I gave you 2 equations on the equation sheet. One is Q is equal to C times delta T. The other is Q is equal to mass times specific heat times delta T. They're both valid equations, but they're not used for necessarily the same thing, and this is why. In this reaction, we're doing bond calorimetry, so our mass term is in our calorimeter constant. We don't need to multiply by the mass. So a lot of people try to take the 4.98 grams and multiply it. But that's not going to work because calorimetry doesn't take that into account. How do I know that I don't need the mass term and I could use Q is equal to C times delta T without remembering that this is my Q calorimeter? Well, I can look at my units. My units of my C, my heat capacity, is 4.25 kilojoules times degrees Celsius. If I set up 4.98 grams times 4.25 kilojoules times over degrees Celsius times my change in temperature, which is in degrees Celsius will cancel out, but grams won't cancel out because there's no grams in my C. So that's how I know that I'm not using that second equation. Because if I was using the second equation, I'd have my gram term in here. If you look up the specific heats of different solids, things like that, you'll see that gram in that specific heat. But with our calorimeter constant, because we're keeping certain things constant, that mass term is not in that. So you're actually not, this is not correct. But if you follow your units, you don't have to memorize which Q equation to use where. If the specific heat has the mass in the units, then use that second one. If it doesn't have the mass term in the units, use the first one. So if you follow your units, you don't have to memorize which equation to use. But it has to do with the fact that in calorimetry, we're keeping certain things constant, so we don't have to have that mass term. So what we're told is we have our C of our calorimeter. I'll just put C cal. And we have our initial temperature. Our initial temperature, it rolls from 29.5 degrees C, so that's our initial, to 69.8 degrees C. Now remember, this is my temperature of my calorimeter, which means that the calorimeter temperature is increasing, which means that my reaction is losing heat. It's giving it up. Because we can't really measure the change in heat directly of our reaction, but we can measure the change in heat of our surroundings, and our surroundings is our calorimeter. So you should already know that my delta E for my reaction is going to be negative, because my surroundings is positive, it's accepting the energy. So again, you're thinking about what's happening. And the reason why we do this, one, we do the bomb calorimeter because it's controlled. We're controlling the surroundings. And two, we can't directly measure the change in heat in our reaction. But we can measure the change in heat of the calorimeter. That's really easy to do. So keep in mind, this is my temperature of the calorimeter. This is my surroundings. So our Q cal is going to be equal to C of our calorimeter, which we're given, times our change in T of our calorimeter. And again, if you're following your units, you'll see that the Celsius term cancels out. So that means we're left in kilojoules. And that makes sense, because we know our heat is typically measured in kilojoules. So that means that our surroundings, our calorimeter, is increasing in energy. But what we need to know is our Q of our system. So we could calculate our Q system, because our Q of our system is going to be equal to our negative Q of our calorimeter, our negative Q of surroundings. So our Q of our reaction, that's our system, is equal to negative 171.275 kilojoules. Now this is how many kilojoules of heat is given off for 498 grams of aniline. But we want to know per mole. How do we do that? Let's calculate how many moles of aniline we actually burned. So we started with 4.98 grams of our aniline. And we know our molar mass, so we can figure out how many moles we actually burned. So we didn't even burn a whole mole of aniline. So that means that we're going to be giving off different than what we see here. So all we have to do is divide that number by our Q system, and that's going to give us per mole. Oops, that's 275. No, that's right. So we didn't even burn a mole, so we know if we did burn a mole, we'd release even more energy. Which that makes sense. So let's and then I just converted it to scientific notation because of the significant figures. This is clear with the 3. And that makes sense, that if we only burned, we didn't even burn a half a mole, we burned a very small amount, a fraction of a mole. So it makes sense that per 1 mole it would be a lot more energy given off. Again, not really hard math, but the key is to follow what you're doing and follow what's asking. And also, if you follow your units, you won't make a mistake. So always write down your units. It really can help you. I don't memorize equations. I just look at my constant, see what units it's in, and figure out how to do it based on what needs to be canceled out. So any questions with that? Okay, let's move on to quiz 8. I don't know why it does that.
That's pretty much calling in the thermodynamics.
I might ask, just because I didn't ask different examples. I can ask different examples. I don't necessarily ask questions that are hugely different, but if I gave an example of it in class, you should be able to do it. These, I try to be in the quizzes as much as I can for the time constraint, as wide array of examples for you to study from. But I can't ask every question on a quiz. And I don't ask the exact same questions. Okay, so here, which of the following is true? The answer is D. So let's talk about why the other ones aren't true. Two electrons in the same orbital have to have opposite spins. They have to have a different set of those 4 quantum numbers. You can only have a spin up and spin down in an orbital, so they can't have the same spin. So clearly A is not the right question. I'm going to skip B because I want to, B and D are very similar. C, if it is possible for 2 electrons in the same atom to have identical values for all 4 quantum numbers, no. At least one of those quantum numbers has to be different. Typically, you could have all the other ones right, and then it's either spin up or spin down, because you can't have 2 of the same spin in the same orbital. So each electron has a distinct set of 4 quantum numbers. At least one of the 4 quantum numbers is different from any of the other ones. Now let's look at B and D, because it sounds very similar. So an orbital that penetrates into a region occupied by 4 electrons is more shielded from the nuclear charge than an orbital that does not penetrate and therefore has a lower energy. Versus an orbital that penetrates into a region occupied by 4 electrons is less shielded from the nuclear charge than an orbital that does not penetrate and therefore has lower energy. D is correct. The core electrons are negative, and they block the nuclear energy. Remember, the nucleus deposits charges in the middle. So if I'm standing here and I try to throw something at you with a Yeti hat, is it going to be more blocked than if you come closer to me and sit in the second desk, or less? It's going to be more blocked. So the more penetration, the less of that blocking you have from the nucleus because it's in the middle. So the answer is D. An orbital that penetrates into a region occupied by core electrons is less shielded because it's more in there with the core electrons. And remember, electrons in the same energy orbital aren't shielded from each other. So it's just the inner ones are shielding the outer ones. So the more you get in, the less blocking you have, and therefore that's why sometimes the D orbitals in a higher energy level are lower in energy because of that penetration. So just think about what's happening. And in the center, so the electrons closer to the nucleus is blocking the nucleus energy from getting to the electrons more outer. So understanding those kinds of things from chapter 7 is what I want you to be able to understand. Which of the following occurs as the energy of the photon increases? Well, the wavelength gets shorter. Remember, as our frequency gets higher, our energy increases. And as our frequency is higher, our wavelength is shorter. Not really talking too much about the speed. We might be able to assume that the speed increases, but there's more going on with speed. So we can't just make that assumption. Okay, so for n equals 3, what are the possible sublevels for L? So L can be up to n minus 1, from 0 to n minus 1. So if n is equal to 3, that means L can be from 0 all the way to n minus 1. So that's 0 to 3 minus 1. So 0 to 2. So that could be 0, 1, and 2. So that's D. Now, ML would be E, if I was asking what ML would be. ML can be our L from negative to positive. So negative 2, negative 1, 0, positive 2, positive 1. If L is 1, then it's negative 1, 0, positive 1. If L is 0, then it's 0. So, but I'm asking for L. And what did we do with those? We were able to draw our molecules. So hydrogen, which only has an N equals 1, can only have an L of 0 and can only have an ML of 0. What do we get? A 1s orbital. We can only have the 1. We can only have the s, which is L equals 0, and then s only has that 1 orbital. Versus carbon is in that 2 energy level, N equals 2. So carbon can have an N equals 2. It can have an L from 0 all the way to 2 minus 1. So that's 0, 1. That means carbon has a 1s orbital when L is equal to 0, ML is equal to 0. And then carbon can also have a 2s, L is equal to 1, ML is equal to 0, and a 2p. And that's what we're showing with that. So carbon does have that. And same thing with nitrogen, and phosphorus, and everything else in that N equals 2 orbital. And then we can fill it in with the electrons. But we're not doing that. Carbon has 6 electrons, and then we fill that in. So that's what we're representing with these quantum numbers, our boxes that we fill in later, that we use the periodic table for. Speaking of those boxes, here they are. But this we're only looking at the valence boxes. Oh, I skipped 4. So all those quantum numbers give us these possibilities, which I just drew here with these orbitals. So that's what chapter 7 is trying to get you at. So we want the ground state electron configuration for SB. No, go away. Cancel. Okay. So let's look for SB. And it is right here. Now, you can do the full electron configuration, but I'm not going to make you do that for one who has 51 atomic number, because that's going to be a lot of orbitals. So instead, we're going to start with the noble gas before, because it's going to have that same electron configuration up to krypton. So we're just going to start with krypton. And we just put that in our brackets. Then, after krypton, we go to our 5s, and they're going to be full, so 5s2. This a little bit lower. And then, remember, this is -1, so this is 3, 4, 5, and 6. And we go straight through our D. So that's our 4D, and of course there's 10. There's 10 boxes, there's 10 electrons. And then we're back up to 5 here. It's only the D that's -1. And then that's of course our P, and we have 1, 2, 3 boxes, so P3. So that's our configuration, starting with krypton, and then 5s2, 4d10, 5p3. And this is neutral. If it was a charged sp, then we would either add electrons or take away depending on the charge. If it's negative, we're adding electrons. If it's positive, we're taking them away. So that's B. C looks right, but remember it's -1. So this is 4. And then xenon is the noble gas after it. But we're using the noble gas before it because it's going to have the same electron configuration up to that point. Now here's the valence orbital diagram for selenium. Again, let's look back at our periodic table. Selenium is 34. So we have our 4s. And then we only want the valence, so that's only the n equals the highest number. So that's 4 in this case. So we have our 4s and our 4p, and then of course that's not going to give us AB. Now the difference between D and C is, remember, we fill the lower energy orbitals first. So that means that our s orbital is going to be filled before we go in and we put electrons in our p orbital. So we're going to fill it, and then our p orbitals, we do not pair until all 3 of our p orbitals have 1 electron in it, and then we pair. So that gives us D. 3 is incorrect. Well, there's not enough electrons, and A is not correct. There's not enough electrons, and of course we're not at a 3p. B is wrong because that's actually the electron configuration of the element under selenium, and that's sulfur, because that's 3s and our 3p. They look very similar, but they don't have the same N. But we do see similar bonding patterns between them because their valence orbitals look similar. Here we're looking at atomic radius. So again, we want decreasing, so biggest to smallest. So let's look at our periodic table again. And we are looking at rubidium, 37. Erase that. Comparing that to xenon. Comparing that to argon. So remember, as we go down the periodic table, the atoms are going to get bigger. The radius is going to get bigger because we have more orbitals, so therefore it has to be bigger. We have more electrons, all of that. So argon's clearly going to be the smallest. Argon has an N of 3, whereas rubidium and xenon both have an N of 5. So clearly they're going to be bigger than argon. Argon's going to be our smallest, so you really don't have to compare A, D, or C at all. But then the question is between rubidium and xenon. So even though xenon has more electrons in it, it's actually smaller because we do decrease slightly going across the periodic table. Because xenon, though it has more electrons in it, they have the same energy level, but xenon has more protons in the nucleus. So that means it has more nuclear charge. It pulls the electrons closer to it. So since it pulls the electrons closer to it, it's a little bit smaller than rubidium, which even though rubidium only has 1 electron, it only has 1 electron in the nucleus, so that 1 electron can kind of get a bit further. So the biggest is going to be rubidium, then xenon, then argon. Is it a lot bigger than xenon? You'd have to look at the numbers for that, but you can follow those trends. So the answer is E. But I did give some credit for B, because you knew argon was the smallest. Yep. Because as you get the bigger effective nuclear charge, it pulls the electrons closer to it. That's why we have a slightly, our atoms decrease going across the periodic table. And you can also think about the fact that we didn't learn this at this point, but now we know it. That as we go closer there, we have more electronegativity. So fluorine is the most electronegative. It's also one of the smallest because it pulls those electrons closer to it. Well, hydrogen's smaller because it has less orbitals. But electronegativity, and the electronegativity is coming from the fact that we have more protons in the nucleus as we go across. So that's why electronegativity increases going across, because we have more effective positive nuclear charge. And remember, our electrons are attracted. The main thing in most of chemistry is positive charges and negative charges attract each other. Have a good night.
You too.
Okay, so let's look at some more thermodynamics. So here we're looking at Hess's law for this one. We can put it together. If we can take these two chemical reactions and manipulate them and add them together to somehow form this original reaction, whatever we did to these, we can do to the delta H of those reactions, and we'll get the overall delta H. We can calculate delta H of a reaction in multiple ways, and this was one of them. So, what we can do here, let's look at the reaction. Let's start with NO2. NO2 is our reactant. If we look at, actually let's start with this one. In our reaction we're trying to get, we have NO, and NO, we have 2 moles of it in the product side. So that's true of this reaction. We have NO. NO is only in the product side, so we can just rewrite this reaction exactly as it's written. It's unlikely we have to multiply by anything because we have 2 moles of NO in this reaction and we have 2 moles here. We don't want to start with looking at O2 because O2 is in both of our given reactions, so that one's kind of hard to work with. But NO is only in that first one. So we know that all of our moles of NO have to come from that first reaction. So I'm going to write that down. N2 plus O2 . And I didn't do anything to the reaction, so I don't have to do anything to the delta H of that reaction. Now, if we look at the second reaction here, we see that, again, we have O2 in this reaction, but we don't want to look at O2. That's going to be harder to solve with because it's in both reactions. But NO2 is only in this reaction, so we know that all of our moles of NO2 in our final reaction have to come from that second given. But our NO2 in our second reaction is in the product side, but our NO2 should be in the reactant side. So we're going to flip the entire reaction. There we go. And when we flip the reaction, that means we have to flip the sign. I'm not done though, because I need 2 moles of NO2. And I only have 1 mole of NO2 right here. So I'm going to have to multiply the reaction, the entire reaction, by 2. And when I do that, I also have to multiply this by 2. So I'm done. I really don't have to do anything else, but I like to double check to make sure that when I add these 2 reactions together, they do equal to my final reaction as it should. So I can add my 2 NO2. Now I have 1 mole of N2 gas on one side of my arrow, and then I have 1 mole of N2 gas on my other side. They can fully, 1 mole minus 1 mole is 0, so they fully cancel out. 2 times 1/2 is 1. Then my O2 O2, I have 1 mole of O2 here, and I have 2 moles of O2 here. So that means that 1 minus 2 is going to leave me with 1 mole of O2. Everyone sees what I did there? Just subtracted. My 2NO, and then plus, of course, I'm left with 1 mole of O2. So does my final reaction equal to the reaction I'm trying to get? And it does. I should have 2 moles NO2 forms 2 moles NO plus O2, and what I found is 2 moles NO2 forms 2 moles NO plus 1 mole O2. So it's equal, so I know I did it correctly. That last step I just did is just to check to make sure that I did everything correctly. So now I know I did everything correctly. I can just add this together. 183 kilojoules plus 2 times negative 33 kilojoules, and that will give me my delta H reaction. Don't forget to multiply it by 2 though. If you multiply the equation by 2, you have to multiply the delta H by 2. If I switch the reaction order, I have to switch the sign on my delta H reaction. So be careful there. Any questions with that? I won't give you a very hard one, but you'll have one like this on the test. Some of the homework ones are much more difficult, but you are have a time constraint with the test. So don't expect one any harder than this one. Okay, here, technically, if you set up the formation reactions, you could do the exact same thing. But you don't have to, because I gave you the delta H formation of each of the molecules in the reaction. So you don't have to, but you could set up the formation reactions and actually do the same thing I just did above. But why give yourself more work when you don't need to? Our delta H of our reaction is going to be equal to the sum of our delta H formation of our products minus the sum of our reactants, our delta H formation. The minus is important, and the orders are important that we're doing products minus reactants. All that's showing is in the reactant side, we have to break bonds. In the product side, we form bonds. So that's representing the fact that breaking bonds takes energy and forming bonds releases energy. So that's why that order is important. Now don't forget though, if we have any of these mole numbers before, we have to take that into account. Because of course, this reaction is saying it takes 4 moles of Fe2O3 to react with 1 mole of CO. So we can set that up. It's going to be 2 times Fe3O4, heat of formation, plus 1. I don't have to put the 1, I'm just putting it right now for this description. CO2, heat of formation, minus, I like to put this in brackets so I don't make a mistake with my signs, 3 times my reactants. So now I just fill this in from above. So my Fe3O4 is negative 1,118. And this is all kilojoules per mole. I'm not going to write the units because they're all in the same units. Plus my CO2. I like to put it in parentheses so I don't lose my sign. It's really easy to lose a negative sign here. So you got to be careful with your calculator. Minus 3 times my reactant Fe2O3. Plus, of course, 1 times CO. And I'm just putting it in brackets because remember, this is a subtraction sign, so I don't want to lose that sign. It's really easy to make a mistake with your negative numbers here. So when I put this and I calculate it, it comes out to negative 47. Make sure you can put this in your calculator and you do get negative 47. Otherwise, you're putting it in your calculator wrong because it's set up correctly. So don't lose those signs when you're setting it up. We actually learned one other way to figure out our depth H formation if we know our bond association energies, which we just learned in the last class. So we have multiple ways we could calculate our delta H of a reaction. And this is kilojoules per mole, of course. Okay, so lastly, the quiz from, was that yesterday? Yesterday. And I'll have them graded soon. I just had a lot of other things going on. But that's okay, we're going to go through it. Okay, so first off, I'm going to give everyone a point for this question because I don't know if someone answered C with the right answer or if someone answered C and was thinking the wrong answer. So I'm giving everyone a point. But the actual answer is C, oxygen. The actual answer is oxygen. Our paramagnetic means we have at least one unpaired electron, so it acts like in a magnetic field, it will align with the magnetic field. So you could draw out the valence orbitals for all of these. You really don't have to, though, and I'll explain why. We could just draw out oxygen, but you really don't have to draw out all of them. So why am I saying that? Well, answer B is argon. Argon is a noble gas. A noble gas has a full octet, so therefore it can't have any unpaired electrons. I don't have to draw that out. I know that because I know noble gases have a full octet, and therefore no unpaired electrons. You can draw it, but that's true. It's because I know that about a noble gas. Ti4 plus, here's titanium. Oh, where are you? Here you are. Ti4 plus, it has 1, 2, 3, 4 electrons in its outer orbital. If it's Ti4 plus, that means it lost all 4 electrons. So what does Ti4 plus look like? Xenon. Does xenon have any unpaired electrons? No.
I think TI is number 22.
Oh, I'm sorry, yeah. But it has 4 paired electrons. It's actually argon as well. Either way, it's a full positive charge, and it looks like the noble gas before. Because that's what our metals form ions for. So you could draw it, but that's what it looks like. It looks like argon. So oxygen's the only possibility. If oxygen wasn't paired, then none of them would have an unpaired electron. So oxygen has our 2s and our 3 2p. And oxygen has how many valence electrons? 6. So 1, 2, 3, 4, 5, 6. Yes, but I'm asking how many total valence? I know. Me too. I just said titanium was 81, so I hear you. So clearly we have 2 unpaired electrons. We could actually also show that based on our Lewis dot structure, which also has 2 unpaired electrons. So our Lewis dot structure actually shows that pretty well. At least for most of our main group nonmetals. That's kind of what our Lewis dot structure is representing, what the valence electrons look like in the orbitals. But B, we didn't need to draw, and A, we didn't need to draw. But I'm giving everyone a point for this one anyway, because I don't know if people chose C with the right answer, or people chose C the wrong answer. So sorry about that, but yeah, you each get a point.
So what's the difference between paramagnetic and
In the diamagnetic, we have all paired electrons. Paramagnetic, we have at least one unpaired.
so like paramagnetic, like it's like an odd number.
No, not necessarily. It's all about how many are paired. Well, it can be an odd number. It doesn't have to be. This has 6 valence electrons, but it has 2 unpaired. So it depends on when you draw the diagram.
All right.
So it's as long as you have 1 unpaired. So I guess if it's completely paired, it would have to be an even. But it doesn't have to be an odd number. This is 6 and it has 1 unpaired. So it depends on how you fill the orbitals in. So here we're looking at first ionization energy. First off, you need to understand what first ionization energy is. The energy it takes to get to that first ion, so to remove an electron. So let's look at our examples, or not our examples, our atoms. So we have rubidium, we have potassium, and we have calcium. So rubidium has more orbitals, a lot more. So when we're going down, we have more of those orbitals, and therefore we have more electrons blocking the effective nuclear charge. So as we go down, it's easier to remove that electron because it's not getting as much of the nuclear charge. So when we're going down, we're looking just at the fact that there's more electrons and it's lost. Now when we're comparing potassium and calcium, well, calcium does have more electrons. They're in the same orbital as the potassium ones because they have the same end. So the valence electrons are both in the same end. And remember, the electrons in the same orbital don't block the nuclear shield. So it doesn't matter that there's more electrons. What matters is calcium has more positive charge in the nucleus. So when we're directly comparing 2 atoms in the same row, the atom that has more electrons in the nucleus is going to be harder to remove that electron. You could also think about the fact that the atom that's more electronegative, which means the atom that has more electrons in the nucleus, is harder to remove that electron. So when we're going down the trend, we're looking at is the fact that we have more electrons. When we're going across, we're looking at the effective nuclear charge. Because the electrons in the same orbital don't really block the nuclear charge. So the more positive charge we have, the harder it is to remove that first electron. So, of course, the answer is rubidium is the easiest because it's bigger. And then we have potassium's a little bit easier because we only have 1 proton in the nucleus. And then calcium's a little bit harder because we have 2. So as we go across versus down, the trends are opposing each other. But if you think about what we're doing, which is moving the electron, it makes sense. Now here we're looking at radius, and again, you don't really have to memorize these trends. If you understand what's happening, it makes sense. So first off, I usually look at a periodic table. We really don't need to, because when we form all of these charges, we basically all make the atoms look like the same noble gas. So even though calcium does have, bless you, 1 higher N than our other ones, phosphorus and sulfur, when calcium loses its electrons, it looks like argon, which has the same N as phosphorus and sulfur. Did everyone see that? So when calcium forms its ion, it actually has the same outer orbitals as these, at least where the electrons are in. So let's just think about what happens when we form a charge. So when we form a cation, we lose electrons. How does that affect the electrons that are left? Because calcium still has electrons left. We only lost the 2 valence electrons. Well, the way that affects the electrons that are left is, let's just draw this with an example metal. Let's say the example metal has 2 electrons in 1 orbital, and I know this isn't really how the electrons exist in the orbitals, but I just want you to think about it. And then that's a metal. metal looks like this. So that means we have 12 protons, 12 with positive charge. So we lose those 2 valence electrons. So now we have 12 positive charges in the nucleus, but now we only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total negative charge. So that means we have more positive charge in the nucleus than negative charge, so that means all of our electrons are getting more nuclear charge. What does positive charge do to negative charge? It attracts it. So when we form an ion, that means that these electrons are going to be pulled even closer to the nucleus. So when we form a cation, our atoms get smaller. Because now we have more positive charge in the nucleus and less electrons shielding each other, so it pulls it closer. Because we have a lot more of that positive charge and negative charge. So cations get smaller compared to the neutral compound. What do anions do? Well, if we look at a nonmetal, I like that I can see my lights reflecting on the board and makes me happy. So let's say this nonmetal has this many electrons, so that's a 7 plus, 9, sorry. And then we gain another electron. So now we have 10 minus. Now we have less positive charge in the nucleus. So those electrons are not going to feel the charge as much. So the atom is going to get bigger. So the bigger the negative charge, the bigger the atom. The bigger the positive charge, the smaller the atom. And again, it's all about what's happening. If you can understand what happens when we form these ions, it makes sense. You don't have to memorize the Trinity. And they are comparable because they all form the valence to look like the same noble gas. So of course, our smallest is going to be calcium 2 plus, followed by Cl minus, followed by S2 minus because it has the most negative charge. This one would be a 1 minus. If we had a 2 minus, it would be even bigger. Okay, so remember, I dropped the 2 lowest quizzes, and when I put these quiz grades up, I'll make Moodle do that. Moodle's not dropping any of your quizzes right now. But once I put the last quiz grade up, I'm going to make Moodle do that. Okay, so looking at this Lewis dot structure, we have 5 valence electrons. We want to put our electrons on each of the 4 corners first before we pair. So that's 4, and then 5. So our correct Lewis dot structure is 8. It doesn't matter which of the corners you have the lone pair on, but you're going to have 1 pair of electrons and 3 unpaired. And that explains nitrogen's neutral bonding patterns. So when nitrogen bonds and it's neutral, it typically bonds in this pattern. Okay, so for this one, you have to know a little bit about lattice energy and then a little bit about melting point. So the more stable the crystal, the harder it's going to be to break that up to allow it to melt to get into the liquid phase. Because remember, ionic compounds are typically solids at room temperature. So what this is essentially asking is, which has the largest lattice energy? Which is the most stable crystal structure? That's really what this is asking. Because the more stable the crystal structure, the higher the melting point. The least stable the crystal structure, the less energy it's going to take to break up that crystal structure and allow it to go into the liquid phase. The more stable, the more heat it's going to take to make it go into the liquid phase. So this is really just asking which has the most stable crystal lattice. So remember, the bigger the charges, the more stable the crystal lattice. But all of these have the metal being +2 and the non-metal being -1. So we're not looking at charges at all because they're all exactly the same. So instead, what we're going to look at is the actual bond lengths. The shorter the bond lengths, the shorter the distance between the, it's not really a bond length, but the shorter the distance between the ions, the more stable the crystal lattice. So that's the question. And the answer to that is, what's the smallest atoms that we have? Because they're going to be able to get closer. So we're looking at our halogens. Fluorines are our smallest halogens, so we can just cross out everything else besides B and D, because all those other halogens are bigger. So they're not going to get as close. So now that we know fluorines are our smallest halogen, what's the difference between magnesium and strontium? There you go. Magnesium, strontium, magnesium is smaller. So MgF2 is going to be our most stable crystal lattice, and that's going to be, therefore, our highest melting point. Now remember, the bigger the charges, the more stable, and that's going to be a bigger effect. But in this case, they all have the same charge separation. Least polar, A. It doesn't matter that fluorine is the most electronegative. Polarity is the difference in the electronegativities. So two atoms bonded together that are the same has a zero difference in electronegativity. Okay, here, what's our formal charge? It should have 5. It has 0 lone pairs. And it has 1/2 of 8 electrons. There's a total 4 bonds, so that's 8 electrons. So that's 5 minus 4, and that's plus 1. Anytime nitrogen has 4 single bonds, it has plus 1 charge. Carbon is neutral. In this molecule, oxygen has a -1. Make sure that you can calculate that. Hydrogens are all neutral, clearly. Hydrogens have 1 bond.
So for the formal charge, you take the valence electrons.
The formal charge, you want to know if you were to break the bond and 1 electron went on one atom, 1 electron went on the other. You did that for all the bonds to that atom. Would you have the valence electrons that the periodic table predicts? Now, if we have lone pairs, they're clearly sticking with that atom. So to calculate our valence, to calculate our formal charge, it's the amount of valence electrons that should be on the atom. We get that from the periodic table, that never changes, minus all of our lone pairs. If this was oxygen, that would be 1, 2, 3, 4, 5, 6. So oxygen should have 6. It has 6 lone pairs. And then minus half of the bonding electrons. So we have 1 bond, so that's 2 electrons. How do I know it's -1 just by looking at it? Because when oxygen has 3 lone pairs and 1 bond, it's always -1. Because when you look at these enough, you just learn the patterns. But you can always calculate the formal charge. The valence electrons the periodic table predicts is always the first number, because if we have more electrons than what the periodic table predicts, what charge is an electron? Negative, so it'll have a negative charge. If we have less electrons than the periodic table predicts, what charge is electrons? Electrons are still negative. So that means we have less, so that means it'll have a positive charge. So that's why the number of valence is the first number. And that never changes per atom. Oxygen always has 6, carbon always has 4, nitrogen always has 5. That's from the periodic table. Now you don't need to necessarily memorize this, but like I said, you kind of get used to the carbon that has 4 bonds is always neutral. But you can calculate it, it would be 0. Any questions about formal charge? Let me do this one down here. So NH4 plus. So first off, this one's pretty easy, but let's go through. I'm going to go through 2 ways to do this. One is, let's go through the way we went through in class, but the other way we'll look at the dot structures. So the way we went through in class is that nitrogen should have 5. And we have 4 hydrogens, and each hydrogen has how many valence electrons? 1. So that's a total of 9, but we have an overall positive charge. So that means we have 1 less valence electron than the valence is predicting. Remember, electrons are negative, so if we have 1 less electron, we're going to have an overall positive charge, because the number of protons in the nucleus never changes. The number of electrons can change, the number of protons in the nucleus doesn't change, so therefore, we have less electrons, it means we have a positive charge. So it means we have a total of 8 electrons. We put our nitrogen in the middle, because it's, well, it has to be, hydrogens can only have 1 bond. But it is the most, we don't have any other electropositive ones. So nitrogen has to be in the middle, that's our only choice. Hydrogen can only have 1 bond. Now we're going to bond those. We used 8 electrons, so we used all of our electrons. This is literally what it looks like. And actually, with the formal charge, it should have this. But we're showing it with the brackets. So clearly E is the answer. A, hydrogen can't have 2 bonds. Don't even look at that one. Don't look at A, C. Hydrogen can't have 2 bonds. B has a total of 12 electrons. Where are all those electrons coming from? Also, notice nitrogen actually has 12 electrons surrounding it. And it can't have more than an octet. So that's just wrong because we have too many electrons, but it's also wrong because nitrogen can't have an expanded octet. So it cannot have more than 8 electrons. So that one's very wrong. D is also wrong because nitrogen can't have 10 electrons, and it's also too many electrons. So actually the only possible answer is E. Everything else violates our rules. Now if you were doing this looking at the valence electrons, putting it together actually makes sense. Because we have a positive charge, we took away one of the electrons of nitrogen. So we would form a bond between here, and then all of our things have either a duet or an octet. Okay, and one more example from this quiz. Everyone should have this answer right, because if you look at the periodic table, you should be able to get Al2O3. That's based on, from like what, chapter 2? But explaining it with Lewis structures is really what I wanted to get from this. Now remember, we don't really show covalent ionic bonds with a line. That's reserved for sharing of electrons. Unless if we have one of those bonds that are kind of between ionic and covalent, we typically show it with charges and not with a line. So don't draw lines in your pure ionic compounds. So what we have is, we have aluminum. And aluminum has 3 valence electrons. And we have oxygen. And oxygen has 6. So as you can see, our aluminum can give up 1 electron to oxygen. It can give up a 2nd electron to oxygen. But then it still has an electron left and oxygen can't accept any more. So another oxygen has to come in. That aluminum can give up an electron to oxygen, but now our oxygen doesn't have a complete octet. So another aluminum has to come in. So this other aluminum can come in, and it has to give up 2. Of its electrons. Ooh, not 2, 1. Putting too many arrows there. It's not nitrogen. So our other aluminum still has 2 more electrons. It's still not stable. Can't just throw electrons into the air. So it has to go somewhere. So a 3rd oxygen has to come in. And now all of our oxygens look like this. And all of our aluminums look like this. So that's why we need 3 of these and 2 of these. Okay, now I do have, you can stay if you want, it won't take long, it's not a lot. But I do have 3 examples from problems like what we learned in last class that wasn't on the quiz. And I like to go through these so you have some examples to go through. Specifically resonance and this delta H I really wanted to go through. So if we're choosing the strongest bond, the more electrons shared are going to be a stronger bond. So NO and N double bond O and N double bond N both have 4 electrons versus these only have 1. So between A and E, those are going to be stronger. They're going to be shorter, they're going to be stronger. Now the question is, which is going to be stronger between NO double bond and NN double bond? And the answer to this one has to do with size of the bond. Oxygen is more electronegative than nitrogen, so it's slightly smaller. So that means the N triple bond oxygen bond is slightly smaller than the N double bond N bond, because these 2 nitrogen is bigger than oxygen. Is it a huge difference in size? No, but it's enough to where we have a difference in strength. So the smaller, the shorter the bond, the stronger the bond. So the shortest bond is N triple bond O, followed by N double bond N, minus the triple bond, N double bond O. And then if we were looking at these are all shorter than those 2, but then we could again look at size differently. So iodine's pretty big. It's lower down on the periodic table. Sulfur is pretty big. Oxygen's the smallest. So of these 3, this NO bond is going to be a bit stronger. But the double bond is going to be the shortest. So those 2 are what we're comparing. The single bonds are going to be weaker. It takes more energy to break 2 bonds than it does to break 1 bond. Now let's look at another way to do delta H. Here we're looking at breaking bonds. Now for this one, it really helps to draw the Lewis structure. So our Lewis structure for CH3OH, our hydrogens have to be at the end. So we have, and I kind of have this one set up, and we do that sometimes in organic chemistry, where instead of putting CH4O, I'm putting CH3OH to specify one of the hydrogens is directly attached to the oxygen. So that's why sometimes you'll see sometimes the hydrogen not all in one place. So the actual chemical formula is CH4O, but this chemical formula represents the connectivity a little bit more, which is that 3 of the hydrogens are attached to carbon, and 1 of the hydrogens are attached to oxygen. That's really the only way to put this molecule together anyway, but when you have longer carbon-containing compounds, sometimes this helps explain how it's connected. So remember, carbon, we have 4 electrons. We have 4 hydrogens. They each have 1. And then we have 1 oxygen, and that guy has 6. So total is 14. And it's all neutral. So our hydrogens have to be at the end. So that means our carbon and oxygen have to be bonded together. Carbon can have 3 other bonds because it can't have an expanded octet. And then, of course, that other hydrogen has to be attached to the oxygen because, again, we can't do this with hydrogen because hydrogen doesn't have a 4 bonds. So this is really the only way to put it together. And we do have 2 lone pairs left on the oxygen. So that's what that looks like. Our O2. The lone pairs aren't important for this, but it is important to draw out the structure. Our carbon is in the middle for CO2. Plus our oxygen for H2O. And you really want to go through and make sure you can draw all those Lewis structures. They're all simple Lewis structures, so you should be able to draw those pretty easily. Okay, so in our starting material, we're breaking bonds. And in this case, our carbon in our final product doesn't have any hydrogens, so we have to break all 3 of those. Oops, I forgot this. Let's not forget that. We also have to break the carbon-oxygen bond because it's not a single bond in our product. And lastly, we have to break the hydrogen-oxygen bond so it can reform to form water. We only have 1 mole of methanol, CH3OH, that's methanol. So we don't have to worry about multiplying that by anything. So remember, it takes energy to break a bond, so all of these are going to be positive. 360 for our carbon-oxygen single bond, and our hydrogen-oxygen single bond is 464. But we're not done because our final product does not have a carbon-oxygen double bond, so we also have to break that. And that is 498. Now, note we have 2 carbon-oxygen double bonds because we have 2 moles of it for 1 mole of methanol, so we do have to multiply that by 2. So total is going to be, our total cost is going to take totally 3,062 kilojoules per mole of energy to break. Now we have to form. Forming releases energy. So we're not forming as many bonds, we're forming 2 CO2 bonds. So C double bond O, 799, and we're forming, so that's negative. And then we're forming in each oxygen molecule 2 OH bonds. Now don't forget, we have 2 moles of water, so we need to multiply each of those by 2. Because we do have to take into account the stoichiometry. So when we add that all together, remember, all of those we're forming, they're all negative. It all releases energy. So that is negative 3,454. Now to get my delta, all I have to do is add those 2 numbers together. 3,062 plus negative 3,454 is equal to negative 392 kilojoules. So you do have to take the moles into account. And you don't have to memorize this or do this. That's not necessary. So the last thing is resonance. Here's our material. We want to know, here's our Lewis structure for some starting compound. We want to know which of these is a valid resonance structure. So first off, our resonance structures have to have the same connectivity. So B is out. Because here we have a CH3 attached to nitrogen. Here we have a C, a nitrogen, and an H. That's not right. We don't have an H attached to our nitrogen, so we already have different connectivity. So if the connectivity is different, it's not a resonance structure. No matter what else. The connectivity is different, it's not a resonance structure, it's just a different isomer. So, different compound. Has the same, it has the same formula, but it's not connected the same, it's not the same compound. Also, we can put A out. There's 2 reasons. One, we have too many hydrogens in A. If we have more atoms than in our starting structure, it's not a resonance structure. The other thing is, we have to have the same electrons. So our overall charge should be equal, and A has an overall charge of positive, and our first structure has an overall charge of 0, neutral. So not only do we have too many hydrogens, but we don't have the same amount of electrons. So this is an example of a chemical reaction where we protonated nitrogen. That's actually acid-base chemistry. So that's not an isomer. I mean, a resin structure. Resin structure is not a chemical reaction. So between C and D, both C and D have the right amount of electrons, the same connectivity. If we look at our starting one, we have a total of 30 electrons. Here we have a total of 30 electrons. Here we have a total of 30 electrons. So we're good there. Our connectivity is the same. But in this structure, carbon has a negative charge and nitrogen has a positive. Nitrogen does not have an octet. In this structure, carbon doesn't have an octet and nitrogen does. Carbon's positive, nitrogen's negative. Nitrogen's more electronegative than carbon, so the better resonance structure is D. Because the more electronegative atom is, the definition of electronegativity is it attracts electrons. So the electrons are actually more stable on the nitrogen with the carbon having not a complete octet. And we represent that by showing the electrons from the double bond going just on the nitrogen. Now overall our charge is the same, +1, -1, and 0. So this one I would have given some credit for, none for these because these are not even resonance structures at all. If y'all have any questions, let me know. Otherwise, have a good night. I hope this helped. Be careful going home.
Everybody cool.